All right, so we're ready to start talking about what are called confidence intervals. And for now, we're going to be talking about a population mean. There's other types of confidence intervals that we can look at. Okay, and so the idea is that we have some random variable x, it is quantitative, all right, and we want its mean is unknown. Okay, that's important. All right, if you know a population mean, you don't need any of this stuff. So this is only in the case where population mean is unknown. Okay, but the idea is that you do want to find or at least estimate it and get an idea. So there's a natural idea to do here. You take a random sample of n independent measurements, okay, and so you get this sample here, and then what do? You compute the sample average or the sample mean. All right, and we know how to compute that, and we usually use computers to do that. So, what's the idea? Is that if my sample is good, and basically if I've sampled enough measurements where I feel like I have a good representation, then what should happen? That sample mean should be close to the population mean. All right, and so like I said in a previous video, uh, X bar is called a point estimate for mu. Okay, and make sure you realize stuff that we've already talked about. If I go and take another sample, I'm probably going to get a different value for X bar. So X bar is a random variable depending on my sample. But the idea here is that at least I have some idea about what that population mean is. Okay? The problem is there's these basic questions that is X bar too big or too small? Okay? Like that. And the other basic question is how far off is it? All right, and so those are the two basic questions that we need whenever we're using a point estimate. We don't know how good it is, and we don't know if it's an overestimate or if it's an underestimate. So what we're going to do is we're going to form from the mean. We'll also use the standard deviation, but from the mean, we're going to form an interval of two numbers, and the idea is that the mean should be within that interval. Okay, now because of everything being statistical and having to deal with randomness, we're not ever going to be guaranteed that the interval we form is going to contain that population average. We'll only be able to assure it with a certain amount of confidence, and so that's the reason these are called confidence intervals. Now, just recall some basic facts that we already know that if n is sufficiently large, then the central limit theorem is in effect. Okay, so what does that mean? That means that x bar is approximately normal with these parameters. So remember what that really means is that the mean of x bar is the same as our original mean. Now remember, that's what we're trying to find too now. And then the standard deviation of x bar is the original standard deviation divided by the square root of n. Now, to start seeing how we're going to do this, let's look at this question. It might seem unrelated, but it's going to be an important question here in a minute, and I'll explain why. Hopefully, you've already answered this question in the homework, but let's look at the standard normal random variable for a minute. Remember, it has mean 0 and standard deviation equal to 1, and we're trying to find the values of z that give the middle 95% of its distribution. So if you remember how to do this, we're looking at this area in the middle as being 0.95, like that. All right, and then we need these tell areas out here. We need to know what these two tell areas are right here. And so remember, we've used up 95% in the middle, so the remaining is 1 minus 0.95, which is 0.05. And then we need to divide that evenly among the tells. And so we get 0.025 in each tell. All right, and so we know the area right here and right here, each one of those are 0.025. And so if you remember how to find Z1, it's just the inverse normal with the tell area of 0.025, mean 0, standard deviation equal to 1, and that comes out to be negative 1.96 whenever you compute that. All right, and the nice thing about the standard normal is it's not only symmetric, it's symmetric about 0, so that automatically tells you that Z2 is going to be positive 1.96. All right. Now, why is this an important question to ask? Is what this is saying is that 95% of the time, a standard normal variable z, it takes values between 1.96 and negative 1.96. Okay, so if I looked at samples of a standard normal variable, 95% of the time it would take values in between those two numbers. All right. Now, the other important thing, too, is what is the standard normal? The standard normal is a standard measuring stick for all normals. If you think about it, all normals are shaped the same. They're just a little flatter or a little more steep, but they all behave basically the same. And if you're measuring things in terms of standard deviation, okay. And so what these two numbers are, these are standard deviations, okay, because the standard deviation of the standard normal is equal to 1. What we're saying is that 95% of the time, z takes lands within 1.96 standard deviations of its mean, and that's true for all normals, okay? So all normals, 95% of the time, they take values within 1.96 standard deviations of their mean. That ends up being a very important property. And so what we can do is we can use the standard normal variable to describe the behavior of all normals if we're going to, as long as if we're willing just to talk about standard deviations and being within a certain amount of standard deviations. And that's part of the reason we're going to use standard normals so much. So the big thing to get out of what we just talked about is that 95% of the time, a normal variable takes values within 1.96 standard deviations of its mean. Okay, think about what that means. We've talked about it. We've talked about being within 2 standard deviations of a mean, and that gives the usual range. Okay, and so the idea is that we have, I got to give a little bit more information, but we have that mu minus plus. We usually say 2 standard deviations, so we multiply that standard deviation by 2, but now we're saying 1.96. Okay, by the way, 1.96 rounds to 2, so that's where that rule for the usual range comes from. 95% is usually used to describe normal behavior. Now, here, you got to remember we're talking about a normal variable. So we have a normal variable with mean mu and standard deviation sigma. Okay, and so so if we go and diagram that out, remember what that means. We have this range of values here, and then this middle area right here is going to be 0.95. And so what is that saying? You got to, I know this is a little deep, but what does that mean? You got to remember on the x-axis is my values for my variable. So what it's saying is that 95% of the time that normal variable takes values within that range. All right, now I know this is a long story, but it's important to get all the pieces together. So now let's take this principle that we just talked about and apply it to x bar. So now to be able to use this principle, we need to know that we can use the central limit theorem. Remember, that means that the sample size is large enough. And so, but if we can use that central limit theorem, then we know that x bar is normal, at least approximately, and its mean is the same as the original mean, but its standard deviation is much smaller. We divide it by the square root of n. So now we can apply this same diagram that we used before. Here's the mean. We add 1.96 standard deviations of the variable we're talking about, but we're talking about x bar, and then we subtract 1.96 standard deviations from the mean. And then just again, remember what that means. Down here on the x-axis is the values of my variable. And so that means 95% of the time, the sample average x bar will land within that range right there. And then notice, to land outside of this range, it's pretty rare. There's less than 5, there's a 5% chance it's going to land outside of that range. So it's rare for a mean to land outside of there. So you can be pretty confident that whenever you take a sample, as long as n is sufficiently large and you can use the central limit theorem, you can be fairly confident that x bar is going to fall somewhere in that range. And then the other thing to point out is I'm talking about the mean of x bar, but remember it's equal to the mean of our original variable, which is what we're really trying to find. We're really trying to get an idea about what that is. So if I can use this kind of reasoning to find out what the mean of x bar is, or at least get a good approximation for it, then I've got a good approximation for the mean of my original variable, which is what I'm trying to find. Okay, and then the other thing to point out is remember that this sigma x bar is equal to our original standard deviation divided by the square root of n. That's smaller than sigma. Okay, and so although I drew basically the same diagram, in this diagram right here, the range from here to here is much smaller than in my original picture. So it's actually a pretty good approximation once we see how to do it. I understand if this is a little confusing right now, but we'll get down the pieces. The key thing to try to get out of what I've just been explaining is that for 95% of samples of size n, so remember what I'm thinking about. I'm thinking about taking a sample, computing its average, and then taking another sample and computing its average, and on and on and on. Well, about 95 out of about 95 out of 100 of those samples, x bar will always land between these two numbers right here. Okay, so now think about how you could write that as an inequality. You might want to pause it. I'm going to do it on the next slide. So all I'm going to do is write what I just wrote in terms of an inequality, that 95% of samples of size n. Now, part of this too, we got to realize our sample size needs to be large enough to use the central limit theorem. Okay, but as long as we can do that, then for 95% of samples, they're going to be x bar is going to be between, that's what those inequalities mean mathematically, is going to be between those two numbers that I wrote a minute ago. Okay, and so we just write those two numbers. Okay, like that. Now, I'm going to kind of skip it, but this is an algebraic kind of equation. It's called an inequality, though, because of our inequalities. And so I can manipulate these, all right? And I can do some subtractions, like I could subtract mu of x in all three of those inequalities, etc., etc. Okay, and so I can do some algebra. I'm not going to go through that all, but an equivalent inequality that you can derive going through the algebra is basically that the x bar and the mu reverse. And so I end up getting that mu is going to be between these two numbers. And we're here, okay, like that, all right? And so now what we're trying to say here is that 95%, I'll just say of the time, but it's 95% of all samples, okay? Then the population average that I'm looking for, mu of x, is between those two numbers, the x bar minus 1.96 times sigma divided by square root of n, and x bar plus 1.96 times sigma x over square root of n. Okay, so another way to summarize this too, remember we've done this before, we could say x bar minus plus 1.96 sigma x over the square root of n if I wanted to. Okay, now what this seems a little bit strange, but this actually gives us an interval. It's the interval from one number to another number. So we're starting here and we're going there. So that's an interval of numbers, and it's saying 95% of the time mu is between those two numbers, and that's what we're trying to find. And so that leads into the idea of what's called a 95% confidence interval. And I'll abbreviate that phrase, usually CI. You can see it takes a little bit to write. Okay, and so this is what we're going to compute. Now you might be confused. I know there's a lot of detail here, but the point is this is something that we're computing. We're actually going to take a sample and compute X bar. We're going to talk about this sigma, whether or not we can use sigma or not. Sometimes we have to use the sample standard deviation. But the point is that if I take a sample and compute X bar, then I can compute these two numbers and I can be 95% confident that mu is in between those two numbers. And again, you got to remember, this is what I'm trying to find. I'm trying to get an idea about what mu is. One other thing to point out, people do confidence intervals different ways, two basic ways. But one thing to point out is this quantity over here, the number that you're subtracting and adding on both sides. If you've ever heard the term margin of error, that's what the margin of error is. Okay, and we'll talk more about it in a minute, but we'll usually denote that with the letter E, capital letter E. And so when people report margins of error, they're using some idea like this. It's based on the confidence. You got to remember back in the original part of the story, that 1.96 came from looking at a 95%. So we'll talk about ways to adjust confidence later. But for now, whenever you hear that term margin of error, that's where it comes from statistically. Okay, so we're going to look at an example, and this is where all the vocabulary that we've talked about throughout the term, almost all of it, really starts coming together. Okay, and so the idea here is that I want to get an idea, an estimate of the average number of credits UCC students take in the spring term. Okay, and the problem is that, that's way too big of a data set. You have years in which people have taken the classes and so on like that. So we have a data set, a population data set that's way too big to be able to actually get all that data and then compute the average from it. So I want to get an idea about what it is though. So what I did is I have a sample of 40 students' spring term credit hours. Okay, and I got these two numbers for my mean and standard deviation. Now you got to remember, this is a sample mean and this is a sample standard deviation, but I'm trying to compute something about the population. I'm going to try to use those to compute something about the population. So just to make sure we understand the vocabulary here, as far as what my random variable is, it's the number of credits in spring. I'm going to abbreviate it to save time. But so my variable is the number of credits in spring. What I'm trying to get at is the mean of that variable, okay? And so that's the average credits in spring of all UCC students in all terms, etc., etc. Okay, my data set came from a few different spring terms. All right, and so that's the thing. And so I computed this X bar from that data set, and I got 12.6 credits. All right, and the idea that should be pretty close to what I'm trying to get. All right, like that. So what do I want to do? I want to compute a 95% confidence interval for mu. Okay, and again, I'm discussing a lot of theory. The calculation's actually pretty straightforward. We just use that formula that we got, the X bar minus plus 1.96 times sigma over the square root of n. Okay, so we start filling things in, but there's a technicality here. So X bar is 12.6, and then minus plus 1.96, and I don't know why I wrote 6 a minute ago there, but that should be n in my formula. Sorry about that. So right there. Okay, and so n, I took a sample of 40 measurements, and so n is equal to 40. Okay, like that. And so I'm going to divide by the square root of 40. All right, the thing is, what's the problem here? This, the sigma in the formula, that's the population standard deviation. Okay, the only number I have is the sample standard deviation. So those aren't the same. Remember calculating these, seeing them on our calculators before, they came out slightly different. And so there's another technicality that requires a whole nother story that we won't get into. But notice that n is greater than or equal to 30. And so whenever n is greater than or equal to 30, we can assume that the population standard deviation is close to the sample standard deviation. You got to be really careful about that, though. All right, there's two parts to be careful about. One, anytime you're given a population standard deviation, use it. Don't use S instead. And then two, to be able to replace this sigma with S, okay, you do need to know that your sample size is bigger than 30, okay? We'll use an entirely different distribution whenever we don't have this case right here, okay? But in this case, we can use that sample standard deviation like that. And so now we're almost there. And so we have 12.6 minus plus. And now in all problems, compute this number separately because it's going to affect how we interpret things. And so just remember, that's the margin of error that we're talking about. So see if you can get that computed. Okay, so hopefully you tried that. What you see is that it has a lot of decimal places on it. We get 1.02268 okay? And we got to figure out how to round that thing, all right? And the key thing is look at my X bar, okay? X bar is the statistic, okay? Like that. So is E. The margin of error is also a statistic. Okay, notice that I rounded this statistic to the 10th place, and so I should round this other statistic to the same number of digits, and so that's going to be 1.0. Okay, and so now let's talk about how to interpret things. Okay, so yeah, this just gets out about what these numbers are saying. So remember what we're trying to get at. We're trying to get at the average number of credits by students in the spring term, at least UCC students, okay? And then going through the math, we got these two numbers right here, all right? And there's two ways to interpret it. In textbooks, they'll compute the interval, okay? And so they'll compute the interval. And so they'll subtract 1 from 12.6 to get 11.6. And then they'll add 1 to 12.6 to get 13.6. And so this is called a 95% confidence interval. We'll usually interpret these in words as well. Okay, if you think about it, I don't know how much media and scientific things you read, though, is I can't think of cases where we actually see an interval. Very scientific things where people know what confidence intervals are. You might see this, but if you think about reading and especially polls and so on like that, they usually give margin of error. Okay, and so some people will answer it as our number with the margin of error being 1.0. Okay, now in these cases you have to understand what margin of error is. That means you add and subtract it. It's going to be kind of up to you how you want to interpret these. But the key thing is we do want to talk about how to interpret these, and that's going to be an important part of the whole inferential statistics part, is not just computing numbers, but thinking about what they mean. Okay, now always they'll begin with your confidence, referring to your confidence, okay? That nothing's absolute. We could be wrong. So what this means is that with 95% confidence, okay, we'll talk about other confidences later, okay? And so what you're going to do, it's up to you how you want to do it. But with 95% confidence, you got to remember what we're talking about. We're talking about the average number of credits by UCC students in the spring. Okay, so here you're always referring to the population mean. So we're talking about mu here. So in your wording, whenever I tell you to interpret something, refer to the population average, okay? And the thing is, this is the sample average. It's set. We know what the sample average is. We don't need to try to find it. What we're trying to find is an idea about what mu is, the population average, okay? And so now there's going to be two ways. Like I say, it depends on if you want to refer to the interval or if you want to refer to margin of error. And it's a kind of a pain for me with grade keys because I have to write them both out for you. But so with 95% confidence, the average number of credits by UCC students in spring, way one, you would just keep going as a sentence, but you would say is between and give the interval values. Is between 11.6 and 13.6 credits. Okay, like that. All right. The other way is you can refer to the margin of error. You say that the average is whatever your sample average was, 12.6 credits. Okay, but then you refer to the margin of error. So then you say with margin of error and give the margin of error. And the margin of error has the same units as your average. And so I started to write units, 1.0 credits. Okay, like that. And so it's up to you, like I say, how you want to answer it. To me, this is more what we see, especially in the media and in a lot of technical journals too. But it's a little misleading because it's kind of saying, yeah, I know what the population average is, and so we don't know what it is. We have to acknowledge that there's some error here. There's two places for error. There's the margin of error place. There's also the confidence part, and we're about to talk about what that actually means in terms of interpretations and what all this is actually telling us. But that's how you compute your confidence interval and then interpret it. The other thing too to mention, to be careful of, is we're not talking about the number of credits. Okay, you can, if you look at data or think about yourselves, there's many students that don't take between these two values of credits. What are we talking about? We're talking about the average. Okay, and so the idea here, again, just to remind you, we're trying to get an idea about what this population average is, mu. And what we just found out is that that population average is between 11.6 and 13.6, okay? But we're not talking about numbers of credits. We're talking about the average number of credits, okay? And so be careful of that, especially in homework and tests. Whenever I tell you to give an interpretation, you're talking about the average. You're not talking about just at numbers of credits. All right, let's talk about what that 95% confidence says. So yeah, we're talking about 95% confidence, and so what the heck does that mean? And so what we need to do is we need to go back to those basic notions at the beginning of the video. All right, so we have to go back to this notion that 95% of all samples of size n have x bar falling in this interval. This is where we got started, right? Like that. So we come back to our picture. I just abbreviated things. So here's the mu plus number, here's the mu minus number. And so 95% of all sample averages fall in this range right here. So 95% of the time, x bar will be in here, okay? And so x bar will land in that range 95% of the time. Okay, but what's the deal? What could go wrong is I could just have a weird sample that falls in this 5% range out here. Okay, 0.025 on each thing. So that's the thing about randomness and taking samples, is that sometimes you just get a sample that's a little bit strange. And so that's what that 95% confidence refers to, is the fact that we're hoping that we got an x bar that was in this range, and in those cases it does capture the mean. But we could have just got a weird sample, and then in those cases we can't be guaranteed that whenever we construct that interval with x bar minus plus 1.96 sigma over square root of n, whenever we construct that interval, we're only 95% sure that that interval actually contains the mean. But there is a 5% chance that we actually didn't capture mu with our interval. So one last thing to remember, if you think back to whenever I was introducing the central limit theorem, we looked at this variable, an exponential random variable whose expected value was 8, and then we took samples. What I did is I just computed the confidence intervals for all 140 of those, or 130 of those samples, and 100% of them contain the mean. Okay, and so Yeah, there is a 5% chance that we won't contain the mean, but in most cases they do. So a little bit of assurance that confidence intervals in general do work. Okay, now we were using a computer simulation, so that could have had something to do with it. But other times in the past when I've looked at this, I very nearly get 100% for confidence intervals. Okay, so I'm going to wrap it up there. But the next thing we're going to talk about is if we want to look at other confidences, and that one will be a lot shorter.